So today I'm going to talk about how we created a faster version of the set cover algorithm and used it in LinkedIn's distributed graph system to reduce the query latency for more than half of the query in our cluster. So here's the outline of my talk. I will first give you a quick introduction of the LinkedIn's distributed social graph. And then I will explain a specific scaling problem that we discovered in our system. I will talk about how we use the set cover algorithm to address this problem, the evaluation of this implementation in our production system, and a few related researches done in the large scale and distributed graph, and the conclusions. So there are many pages on LinkedIn that serves the user's social graph information. For example, this is a search result page. Every single search result displayed on this page is decorated with a social distance. And you can also find out the common number connections between you and each of these search results. And on this page, there's a dedicated search facet right here that you can use to restrict your search result to a desired social distance. And this is the profile page. So every profile page on LinkedIn, you can there is a distance icon, and you can often find a you can often find the number of connections that this user have or the number of followers. And on this How You Are Connected page, you can find out who are your first degree connections, knows a particular person, or have a common connection with that person. And this is a company page. You can find out which one of your first degree or second degree connections work for a specific company, and this can be pretty useful during a job search. So all of those graph information displayed on these pages comes from three major graph APIs. They are get connections, get shared connections, and get graph distance. So the name of these APIs are pretty self-explanatory. I won't go into details for each one of them. The only thing I wanted to point out is more than 50% of the query occurred to our backend distributed graph is to calculate the user's graph distance for a list of member input IDs. And this list of member input IDs can come from a search result page or a group membership page. So basically anywhere that you see on the LinkedIn side shows the distance icon, there is a graph distance query at the back end. So the scalability and the latency for this particular call is very critical for us. So here's an architecture diagram of our backend graph. So essentially, this is a two-tiered system. At the very back end, we have the graph storage layer, which we call it GraphDB. Internally, we use a adjacency list to represent the graph. Because we are storing more than 225 million members and their connections, this data is too big to fit into one physical machine, so we partition them into a fixed number of partitions. Several of these partitions are co-located on one physical machine, and we have multiple replica for each of the each graph copy in our system. Sitting in front of this graph storage layer, we have something called network cache service. So this is basically a ring hash. We use it to store a member's second degree information. So when the member log online, we calculate this member's second degree on the fly. And the purpose of this cache is to basically convert the graph traversal operation into set intersections. So for example, if we have a member and we calculate this member's second degree information, we can find out whether another member is within a second degree apart from this user by doing a binary search on this person's second degree cache. Or we can retrieve this person's first degree connection from the graph, intersecting the second degree cache with the first degree connection, and find out whether this person is within 3 degrees apart from this user. So by doing this conversion, we can reduce a lot of the inter-GraphDB node latencies to reduce the query latency for the graph distance query. At the very front end, we have the API tier. This one is basically responsible to redirect the connection calls into the GraphDB cluster or the distance calls to the network cache service because it needs the second degree information. So in summary, for our distributed graph infrastructure, we have three main components in our system. The very back end is the GraphDB layer, which is essentially the partition and replicated storage for our system. And then we have the network cache service, and the purpose of this cache is to convert the graph traversal operations into set intersections. And then we have the API layer. So what is the scaling problem in our system? Let's take a quick look at how we are handling the graph distance query and how the second degree cache is being created during that process. So first, this call is going to be forwarded by the API tier to the network cache service. The network cache service will look up its local storage to see whether it has this person's cache or not. If it does, then it performs the set intersections right here. If it doesn't, then it will need to build the cache for this user. So first, this network cache service will retrieve this member's first degree information, map this first degree information into a set of partitions, and then it will query the GraphDB node that stores each of these partitions. The GraphDB node, when it's being queried, it will merge its local result into one sorted array before sending the data back. And NCS, upon receiving all of these responses from each of the GraphDB node, it will merge them into one big array, compress it, and store it into the cache, and continue finishing off the graph distance query. So one observation we had when we are expanding the GraphDB cluster is we noticed something like this would happen for the same kind of second degree query. So basically, more GraphDB nodes are now involved doing second degree queries, and each one of them will only return a smaller set of the connections arrays. But on the NCS side, it now needs to handle a much bigger merge. So basically, the work of calculating second degree, the merging now is shifted from the GraphDB cluster into the NCS. So why is this happening? Let's take a look at an example. Let's say I have a member whose first degree connection is stored on 4 different partitions. And I have a graph topology like this. So basically, I have a graph with only 6 partitions, and they are stored on 3 different physical machines. And this 4 partitions requested to return members' connections in this topology will be translated into something like this. So 2 GraphDB nodes will be queried to answer the second degree query. Each one of them will perform a local merge. And NCS will merge these 2 partial results into a second degree cache. So now, if we are adding another replica in our system, each of these partitions now can be served by 2 different machines. That way we can handle failover and load balancing. But in this topology, the same kind of second degree query would be translated into something like this. So as you can tell, even though some of these partitions can be served by just one machine, the load balancer is actually trying to do a good job to load balancing, making sure we don't have a hotspot in our system. So in this case, more GraphDB nodes are queried during a second degree query. Each one of them will have a smaller subset of the results, so they don't do as much work as the earlier topology in terms of merging. And on the NCS side, it will need to do a 4-way merging instead of 2-way merging. So essentially, the scaling problem in our system is when we are expanding the GraphDB cluster, we notice that there is a performance impact, negative performance impact on the NCS side. This is mostly come from increased query distribution and the merging and deduping work shifted from the GraphDB cluster to the NCS. So we look at our problem. Essentially, what we're trying to address here is, given a set of partition IDs, we wanted to locate a smaller set of the GraphDB node that can serve this second degree query. So this is essentially a set cover problem. So I pulled the definition from Wikipedia in case anybody need a refresher. Basically, the set cover problem is you're given a set of elements, which is called the universe, and a family set of S, and you wanted to find out the smallest subset from this set family that can cover this universe. So taking our earlier example, the universe in this problem now becomes the set of partition IDs 1, 2, 5, 6 that stores the members' connections. And the family set S are the partitions from each of the graph DBs in the cluster. And what we're trying to tackle now is to find the smallest number of graph DB node can cover this input partition sets. So the set cover problem is an NP-complete problem, but there is a greedy version of this algorithm available. So basically, the way the greedy algorithm works would be it takes this universe and intersect it with every single element in the set family, and always find the one that offers the biggest coverage. Again, using this example, the greedy set cover algorithm would take the input partition sets and intersect it with every single graph DB node in the cluster, find the one that offers the biggest coverage, and remove the intersection from the input set. And it will continue this a couple of iterations until every single partition ID is removed. Then the graph DB node selected along the way will become the final result sets. So this actually the set cover algorithm, when applied in our system, works pretty well in terms of reducing the number of graph DB node involved in doing these second-degree queries. But we noticed that it actually add a constant latency in our system, because in each of the greedy set cover selection phase, we have to intersect the input partition IDs with every single graph DB node in our cluster. And when we have a lot of these machines in our cluster, we end up spending a lot of time doing the set intersections. So now we look at our system again to try to find out other properties that we have over a general set cover problem to see if we can reduce the number of set intersections that needs to happen in each of these iterations. So let's take a so this is a topology of our graph DB storage. Let's assume that we have one node already selected in one of the iterations, and in the next iteration, one of the partitions I wanted to cover is this partition P. If I only look at one node from each of these replica that stores P, then there are two things I can guarantee. One is at least this new partition P will be removed in this set cover iteration. And the second one is I will be at least looking at one node that offers unlapping coverage from this already selected node. That is because the graph DB node belongs to the same replica do not overlap with each other in terms of the partition coverage. So I used this intuition and I built a reverse mapping from our graph topology. So this mapping is basically mapped the partition IDs, each of the partitions in our graph into a set of physical machines. So basically, using this map, you can find out what are the physical machines that contains this particular partition ID. So now the modified set cover algorithm works like this. Given this set of inputs, I randomly select an element from this set, and I look up only the graph DB nodes that covers this particular partition. So just these two nodes that stores 5, and intersect these nodes with the input set. Select the one that offers the biggest coverage and remove the intersection from the input. So the next iteration, I do the same thing. Randomly select one element from the remaining set. Only perform set intersection between this set with the nodes that stores this randomly selected partition, and select the one that offers the biggest coverage, remove the set intersection. And I do the same over and over again until every single partition is removed from the system, from the input. This is what's produced by the modified set cover algorithm. And this is the original solution without using set cover algorithm, and this is the optimal result set. So as you can tell, the modified set cover algorithm tends to produce a set of nodes that belongs to the same replica. And also in our experiment, this version of the set cover algorithm produces about 1.5 to 2 times of the optimal result set, and it doesn't introduce any additional latencies. So we put the implementation in half of the NCS node in our cluster, and we measure the second-degree cache creation time and the graph distance query time between the set of nodes with the set cover implementation and the ones without. We basically observed almost a 40% drop on the 99th percentile for second-degree cache creation and a 25% drop on the 99th percentile for the graph distance query. Also, the number of GraphDB nodes involved in the second-degree query dramatically reduced. This matches the observation we have that there is a 40% outbound traffic drop on NCS. So this outbound traffic is basically the NCS querying GraphDB node to return connections. So now there are less nodes involved in doing these queries that there is the traffic would also drop. The inbound traffic also drops about 10%, and that drop comes from now less GraphDB nodes are involved in the query, so each one of them will do a bigger merge on their side, so there are more deduping happening on the GraphDB cluster. So eventually the inbound traffic drop about 10%. So during our work, we also look at a few other implementations to address the scaling problem in a large-scale distributed graph. One work that we find particularly interesting is Pujo's scaling through replication. So basically the idea is you always co-locate a member with its neighbor on the same physical machines. That way, all of the second-degree query can be served from one physical machine to reduce the latency. This idea is very interesting, but there is a high cost in terms of replication and reclustering associated with this methodology. So there are a couple work derived from it to address these constraints. And there are also a lot of the innovative parallel graph algorithm are created for the multi-core and GPU system. And again, there are these offline graph systems like Prego or GraphLab. So these systems normally can handle graph with even bigger scale and more complex query, but they don't offer real-time latency, and they use a totally different computation model. So there are, currently at LinkedIn, we have a couple of more efforts going on to further scale our system. One area we're working on is doing an incremental cache update framework. So instead of building a user second-degree cache every time the user logs online, we are working on this incremental cache update framework so that only the delta for a user will be transferred from the GraphDB cluster to NCS. And also, we find the replication ideas being very interesting. We're considering applying some of these ideas in our GraphDB cluster. Basically, we can add like our ucache on these GraphDB node, and every time these GraphDB nodes needs to do inter-node communication, we can always store the result into the cache to reduce future inter-node transportations. And we're also working on a couple of new graph traversal algorithms because there are a lot of new features derived from the application tier. Eventually, not all of these queries can be answered by converting into a set intersections. So to recap, so basically we addressed the scaling problem in our system that happened during a scatter-gather merge when we're expanding our GraphDB cluster, and we applied the set cover algorithm to minimize the query distribution. So if you wanted to read more about the formal description of the algorithm, you can find it in a paper. And if you're interested in coding, this code is actually open sourced. It's available in GitHub. One last thing I wanted to mention is this is one of my proudest work at LinkedIn because this is 100 lines of Scala code, and it was able to reduce the query latency for more than half of the query in our distributed graph system. Thank you.
So for the second degree nodes, you cache the results proactively, or do you, based on the request, or do you do it, proactively before having a request, or do you do it reactively for each request? And for how long do you store those?
Oh, okay. So when the user logs online, the first time they need the graph distance queries, we start building it and we cache it for I think 20 minutes currently, and then we kind of we mark it still.
And if it's done reactively, if you have a 6-degree connection, I'm assuming that would take a long time.
Yeah, we don't. Right now at LinkedIn, we only support up to 3-degree queries, so we don't do a 6-degree.
Thank you.
Out of curiosity, does LinkedIn have a similar policy in regards to open sourcing, like I've heard yesterday from Netflix?
Well, are you asking like what can be open sourced?
Yeah, does LinkedIn also open source their entire code base like Netflix do?
We do a lot of open sourced. We don't like specifically, like for example, the internal graph implementation. We haven't. I think it's not more. We haven't open sourced the internal graph stuff yet. But this is more at the transport tier. So we do open source a lot of these.
Okay. In parts.
Yeah.
Can you talk about more about the new graph traversal algorithm you will be working?
I'm sorry.
Can you talk in more detail about what kind of new graph traversal algorithms you are?
The new kind of graph traversal algorithms.
Mm-hmm. Yeah.
Is that what you're asking?
Yep.
So basically, like so the way that we're handling the second degree information, if you notice, currently we're only building these second degree for the member connections information. So if you're doing like a kind of graph distance, the only thing that you're checking in your graph is the member IDs. But we are also doing a lot of more advanced queries now. So like in our graph, there are new type of entities and addresses in our infrastructure now. So the entity can be like a company or a school, and the kind of graph traversal operations, basically what you wanted to return. Your path not only have just the member, but also other type of entities. But it's kind of become unrealistic that every type of new entities we're adding in our system, we build a new kind of second degree cache just for that particular entity. So we have to do some of these queries on the fly.
Sorry, out of curiosity, since we still have time, do you change the number of partitions when the graph increases?
Yeah. So we actually, at this point, we use the fixed number of partition strategy. We do not. So this is mostly for the simplicity of operation. So we choose this number big enough so that each one of them, there will always be, you can always fit multiple of them into the same box. So when the user base grow and the density grow, we will have to move some of the partitions off from a physical machine, but we don't have to partition the graph.
So your experimental results show that basically your solution is 1.5 to 2 times away from the optimal one. Did you try to actually give some bounds on the performance of the algorithm with respect to the optimal one?
No, we didn't try to do the proofs. Okay. Yeah, we kind of we kind of try the different range of members, like in terms of their size, in our experiment to see how much this algorithm helped us, and we also observed the total number of requests coming out from the node that used the setcover algorithm. So that these kind of matches. For a typical member, I think typical member have like a few hundred connections, and that works pretty well. When you have like a lot of, from the bigger lines, sometimes the results is a little less than the optimal, but overall it works pretty well.